Okay, so uh, reminders, as usual, muddiest point due Sunday. There is a concept check, relatively short one, just like we've kind of been doing with the previous concept check that is due Wednesday. And then the first mini project is due a week from Sunday. And so this concept check is about so the first concept check was sort of about understanding genetic drift is sort of a force that we always have to deal with when we're developing evolutionary algorithms. The second concept check here is more general about the genetic algorithm, the fundamentals of it, which we'll talk about today and which you read about. This first mini project is actually implementing a genetic algorithm using any language you like, a relatively simple one to solve a pretty simple numerical optimization problem and investigate what happens as you change some of those hyperparameters and choices. And this is the one mini project you can't drop. So it's one experience I want you to go through. The rest of the mini projects will be a little bit more open-ended. So we'll go through a unit, we'll introduce a new algorithm. You'll have an opportunity to implement that algorithm and try it out and demonstrate that you've done that. And then there's you think after because of the drop policy on those mini projects, you end up only having to do 2 or 3 of those mini projects after this mini project. So you can sort of pick a unit that you're particularly interested in and then go ahead and implement that. Okay, so it's just darker over here, but I guess it's just those lights. So any questions about these things moving forward? Okay. All right. So we are finally then into implementing this GA. So we're really focusing on the genetic algorithm here and how we tie it to these basics of evolution that we've been talking about, as this is sort of another evolutionary system. And so we've been, saying that our decision vector in our optimization problem. So of course, just as a reminder, the goal here is we have some optimization objective, which might be to say minimize some function that is a function of many of this decision vector, which is just a collection of decision variables. And so that is the design problem, is that you have some criteria that you decide, I want to minimize that criteria. Now, we will shortly get to how do we handle multi-objective problems. And so, but a multi-objective problem will be one in which someone's told you it is like here, someone said, I want you to choose parameters to make this F, so the cost of this design, for example, as cheap as possible. And so I need this to be feasible. I need this to be a drivable car. I need this to be a car that passes all the safety checks. I need this to be a car that can achieve certain minimum performance standards. But I want to do all of that in the feasible set of all the different cars that can do that. I want to do it with the parameters that are the cheapest. That would be one example of an optimization objective. Now, someone might say it'd be great if it was cheap, but we also want it to be as fast as possible. So you could imagine tacking on another one here. Now, they might say, I don't have a balance that I necessarily have in mind, but I just know that our customers like cheap cars and our customers like fast cars. And so you could imagine adding an additional objective in here and then try to simultaneously say minimize one and maximize the other. Now, as we'll get into it, we get to multi-objective optimization formally, without specifically saying one is 50% more important than the other, or so on and so forth. That basically is implicitly saying solve for a trade-off space. So solve for solutions that some that are faster but more expensive, some that are cheaper but slower, assuming there's a trade-off between, or see if there is a trade-off between them. So in that case, these population-based algorithms will be really great because they naturally spit out a bunch of solutions. So I'm only focusing today on a single optimization objective for the genetic algorithm, but I'm going to try to use language that will generalize to multiple optimization objectives, as we'll see here in a second. So this is our goal. This is our sort of engineering design optimization problem. So EDO. And then I'm just going to note formally, possibly multi-objective. And again, when I say multi-objective, a lot of people say multi-objective, they mean an index that sums together multiple objectives. Like a loss function, when you're training an artificial neural network, you might say, I've got this loss from this is my sort of standard loss function, but then I've got this other loss which penalizes this, and this other loss, and I add all those together. Well, once you add them together, it's not multi-objective anymore. It's single objective. How you add them together can vary, but I wouldn't call that a multi-objective problem. That is a way to solve a multi-objective problem is to turn it into a single objective problem. Fine, but don't call it a multi-objective solution. So we will get the true multi-objective solutions here, not in the next unit, but I think the unit after that. But so when I'm saying possibly multi-objective, I'm opening the door for more than one F. So F1, F2, F3, and so on. So that's the general problem. And we want to then build a GA that can solve for this. And so as we've kind of talked about here, then we're going to call each component the decision vector. We're going to call a chromosome. So that's the decision vector. And each component of the decision vector, we're going to call genes. And those are our decision variables. And then each possible value of the genes is going to be called an allele. So if I would say that xi comes from the span of from A to B, then this whole interval, this would be an interval of alleles. So one allele, it might be that x3 is equal to 6. Well, that is the allele. And so that's the language we have to cast that into this genetic approach here. And so this collection, just like the collection of genes is into a chromosome, the collection of alleles is a phenotype. So a particular instance of the decision vector is a genotype. So the collection, so I could say like, if this is like 2, 6, 25 pi, where this is x1, x2, x3, x4, all the way up through our xn. So maybe I'll put comma 2.75, where this is xn. So this is just an example. So this is an example genotype. So that's just an instance, or that's a particular instance of the decision vector. And so these genotypes are candidate solutions. So these are potential ways we could design our system, is by setting up these parameters according to these n variables. And so then, how do we know one solution's better than another? Well, that way we have to evaluate it through our optimization objective or objectives. So that optimization objective, like I said, it can take lots of different forms. It can be a mathematical form, it can be a simulation, it can be a combination of those where you run a sim and then you have to do some math on results from that sim. But there is some way that you can evaluate each one of these genotypes to see how well they're doing. So in nature, the way that's evaluated is you just see how many offspring are produced. So the optimization objective is, emerges from the challenges of just living in that environment. And some genotypes combined in with certain environments are going to produce a lot of offspring, and some are going to put few offspring. And so we need a way to sort of have this optimization objective produce a fitness count that in nature would be a count of offspring, but here it's sort of a proxy for sort of simulated offspring. So so the way we're going to do that is, well, in order to get to fitness from genotype, you got to cross through phenotype. So then the real question is, what is a phenotype in a genetic algorithm? So what we're going to then define is that the F functions that are our optimization objectives, we're actually not going to call, they're not fitness, they're characters. Characters which are, basically different ways in which you can observe genotypes. So it's like, somebody who is observing a car does not observe the design variables. That's the genotype, that's hidden. They observe the performance of the car. So we would call, our optimization objective F. This is a character. Similar to like eye color. In our car case, it could be like speed or cost. And so we could have multiple characters. So I could have like F1 is one character, F2 might be another character. So if you have, multiple objectives, then that means that you have multiple characters. And again, that's like, for example, I might have cost and speed, and those are sort of similar to, say, eye color and height. So um, I'm not directly calling these fitness just yet. Um, it's very tempting to in the single objective case, because they almost are identical to fitness, which I'll get to in just a second. But when we get to multi-objectives, it's important to break them out. And even when single objectives, you can sort of say, well, some things I want to minimize, some things I want to maximize. There might be other ways in which I want to map an optimization objective to a fitness function. Like in an eye color, I'd say, well, there might, maybe an eye color is a particular discrete variable, but the way in which you say that, what's the fitness of blue, or what's the advantage of blue eyes versus brown eyes, this may not map necessarily to just an easy way to say that, that F1 is proportional to fitness. There might be some other mapping that you need to go through the actual values, the range of F1 through, and how you want to penalize them or reward them. So that's why we're calling them characters. These are the observables of your genotype. So each one of these are parameters. So you can have, like, I can say F1 of a particular X decision variable, that is going to then map me to a value that I'm going to call a trait. So I'd say, like, if this is let's say this is a genotype, then the genotype typed through the character gives me a trait. And this is an actual value. So I should say, like, maybe it's equal to, like, 6. So that's the idea of, like, let's say F1 is like, or if F1 is speed, So that is a character. And then if X is, some combination of, you know, some combination of values, and we're going to call that, well, that's the genotype or a candidate solution. Then F evaluated at that particular genotype, that is going to give me some value that, let's say, comes out to 35 miles per hour, and then that we're saying is the trait. So a trait is a character value. And so traits can be good or bad. Some traits can be better than others. Some traits are identical to others. And so the optimization objective is just a way in which we treat as a thing that we can observe and then penalize or reward or ignore. Just like any traits. You can observe skin color, you can observe hair color, you can observe height, you can observe all these different things. Some of these things might matter to you, some of the things might not. And so you can create lots of different optimization objectives. For this neural network, how big is the neural network? I don't care about that. What's the loss of the neural network? Maybe I do care about that. All of these things are functions of the weights of the neural network, but we only actually care about one or two of them as we actually train the neural network. It's the same thing here. So we're going to start out only focusing on one trait or one character when we're talking about single objective optimization problems, but then we're going to eventually graduate to then figuring out how to implement multiple characters, multiple traits. So now that we've got a trait, and then I'll ask for questions here in a second once I define fitness, then we can say we've got some function f, which is a fitness function. And here there is only one, even if there are multiple objectives. And again, we're going to get into multiple objectives later, but I just don't want you immediately to think an optimization objective is a fitness function. We are going to use very loose language where we'll frequently find it convenient to refer to an optimization objective as a fitness function. But that's sort of, we sort of mature into being able to use that loose language because we have to be careful. Very often we want to minimize an optimization objective, but we're going to say, oh, well, that solution has higher fitness. It's more, and then it's going to be confusing because they say, well, higher fitness sounds like we're doing a maximization problem. So, I mean, ultimately, genetic algorithms are always going to be written to maximize this F value, but the mapping from big F to all of the little f's won't necessarily be trivial. But when we're only working with a single optimization objective, a single character, then a lot of times it might be, well, just F is basically the inverse of little f. So if you want to minimize little f, you're maximizing big F. But to allow us the freedom to move to multi-objective later, then we're just going to keep this general and try to put a difference between that. And so we can have lots of little f's, but only one big F. And we need a single big F because, like in nature, it doesn't matter how many different dimensions that organisms can vary. Those are all of their little f's. Those are all of their characters, all of their traits. But they ultimately only have a certain number of offspring. And so that offspring count that they have is a product of all of those characters combined together. So there's only ever one fitness in a genetic algorithm, in an evolutionary algorithm. And that determines how well you move on. How well you move on depends upon multiple optimization objectives simultaneously, but there's only one fitness. So that way we don't want to, you don't want to get into these games where you're trying to pit one fitness against each other, like, oh, they're more fit in this dimension than this dimension. There's no fitness dimensions. there's just different things that contribute to fitness. And because of that, and this is what'll be so beautiful when we get to multi-objectives, is that you can have a equivalence class of solutions that differ in optimization objectives, but are equally fit. So you can say, like, how many different ways can I solve this problem? Well, here is a niche where I solve it with a high-speed car. Here is a niche where I solve it with a low-cost car, and so on and so forth. And then that ends up creating a community of solutions that fill different niches, but they're all equally fit. They will all coexist in the environment, but they will do so with different designs. So that's what we get into. Right now, where, F for a moment is going to look like it's the identical. Big F is going to look like little f, but we want to try to keep general in our heads. So basically, this fitness function, big F here, it is a function of all the little f's. So we have some level of little f's where these multiple objectives all go in, and they all take the same genotype in. This is all genotype. And together, this vector is the phenotype, or it is the collection of traits. And so the fitness function is effectively mapping every phenotype to I'll say a value that can be used for ranking. So I'll say it's a cardinal value. So, but it maps it to I'll say a quality level, which is like, number of offspring. And this allows us to sort solutions. So it lets us create a partial order on candidate solutions. So now you have a candidate solution X, you evaluate all of its different objectives, you pipe their objectives, and you look at that, and I've got, well, it's better in this, but it's worse in this, and all these different things together. So then your fitness function has a way somehow to then blend all of those together and give you one number, and saying that, well, for this solution, its fitness is 5, and this solution, its fitness is 6. And if one of them has a higher fitness than the other, then we say that somehow that genotype that generated that fitness is better than the other genotype. And that's the purpose of fitness, is allows us to move through genotype space, hopefully moving to better and better genotypes, with some genotypes being equally good as other genotypes. And so sometimes our goal will be to find a set of genotypes that collectively are better than all other genotypes. That's what we do in multi-objectives. Here, we're trying to find a genotype that is better than all other genotypes, with still the possibility that there might be many that are very similar to each other. So that's what we mean. So this is, this is fitness, like I said up top, but just to emphasize. And this kind of is the G by E environment. Like, so the environment in a genetic algorithm really shows up through these optimization objectives. So if you change your optimization objectives, you change your environment. So it's just like saying that an animal that is really well adapted for dry environments, they have all the genes that when you put them in dry environments, they're really successful. Then if you drop them into a wet environment, then all of those adaptations that were really well suited for dry environments don't really give them much of an advantage, and they just become costly without any benefit. So then they don't have an advantage in the wet environments. So if you swap F1, this is a dry optimization objective for a wet optimization objective, then it may change the fitness. So this still has that G by E, you get your phenotype by combining your genotype, your design choices with the context. So you can think of, these as the context and, and then these as the designs. And then so the phenotype is a combination of the design and the context, gives you the phenotype. And then with the phenotype, thus the fitness. All right, so any questions about that interpretation? Is the words we use to try to import insight from the processes that go into nature into this design process. Right now, it's all semantics. We just renamed things we already had names for. So it's not that useful, but it maybe helps us think about how we're going to build a meta heuristic to walk through this decision space in a more effective way than just moving around randomly. Okay. All right, so the genetic algorithm, the basic genetic algorithm, it works. I already used up my samples. Okay, so the basic flow. So here's a GA outline flow. In our genetic algorithm, we are going to start with, I'm going to say N genes and M individuals. So I'm going to just model this as a matrix. So imagine that all of these genes can be encoded as numbers that we could put into a matrix. In reality, that's not always the case. Sometimes your genes might be character strings, sometimes they might be binary values, sometimes they might be floats. They can take all sorts of values, and so you might need to use more complex data structures. But you're going to basically need some data structure that collects a bunch of decision variables together, and then some data structure that then bundles all of those data structures together in sort of a vector. So you'll have a vector of individuals where each individual is some collection of decision variables. And and because it's a genetic algorithm, the collection of decision variables, the order does matter because we have these crossover events that we have to define. So it does sort of matter who's next to who. So it's not just like a set of decision variables. But I'm gonna, to keep it simple, just imagine they're all numbers for now. So there's just basically a matrix, and we're gonna say I've got like X11 up here in this corner, and then over here, I've got my first individual and their nth gene, and I'm gonna take that and I'm gonna repeat it for M individuals. And so this is my population of candidate solutions. And so down in this corner, this is going to be XM's first decision variable, XM's nth decision variable, or gene. And everything in between. So there's just this matrix floating around. Again, doesn't have to be a matrix, but for simplicity. Yep. For the basic genetic algorithm, the number of genes does remain the same for all individuals at all time. We're going to talk about in the next unit genetic programming, where we're actually going to use evolutionary methods to write code. In that case, your solutions are lines of code, and they are, not every program is the same lines of code. In that case, then we will actually have genotypes, which every genotype will be a program, and those will vary. And so we have to somehow figure out a way to to take this basic structure that we're about to go through here, which really only works with fixed length genotypes or fixed length chromosomes, and somehow generalize it to chromosomes that can expand and shrink or whatever. Just like, chromosomes in living systems can shrink and grow, and the different individuals and, different species have different numbers of genes and chromosomes and so on. But to start with, it's all fixed. Okay. So we start out with some initial population. So we're just going to generate the initial population. And you typically do this randomly. But if you have some prior information that you want to search around a particular part of the space, you could warm start it there. Typically, if you start up a GA and that's already been implemented for you and you don't provide it any info, it's going to look at you can provide usually constraints on your decision variables, and it will just draw randomly within the constraints. It'll give you a feasible population at random. Okay. And then you go through a selection step. So we're going to select R, and this is a parameter less than M, parents, by fitness. And as some of you see, if you read the perusal chapter, then there's going to be different ways in which we can do selection. And so this is where you will insert or choose a selection operator. So if you start up a GA in standardly implemented GA in a standard industrial tool, they'll have a bunch of selection operators defined. One will be picked by default, probably proportionate selection. We're going to define what that means. And then you can either stick with that, or you can choose a different selection operator, or a lot of programs will provide you a function handle where you can provide your own selection operator. So you got your own way that you want to generate these R parents. That's fine. Give us a function handle. We'll give you the whole population. You give us the R parents out, and then it runs down through here. So this is effectively a hyperparameter that you can set. So then from that, after that selection, then you go on to reproduction, which populates so this generates the next population. And then this is where we're going to have the crossover and mutation operators, which we're going to define. But for those that read ahead. And then from there, we've got our new population. So we can then evaluate how well this new population solutions are doing. And we can see if we've reached a termination criteria. So termination. And this termination criterion might be number of generations. Like it might be, okay, we've got 100 generations, or it might have something to do with convergence. Like the best solution in our population hasn't got any better after 6 generations, something like that. And so if we're done, so if we've terminated, then we can report the final population. And so it's tempting, and let's see if I can get this bar to. Maybe that'll go away now that I've turned that off. There. So if the final population, it's tempting to just report the best of the final population, and ultimately that's what most people will end up using, is maybe the best of the final population. But sometimes if there's a bunch of solutions that are all very similar in fitness, but they vary in kind of other ways, it can be valuable to keep them because there might be something that says, well, that actually, that, because remember, these are all heuristics. These are good, but they're not maybe the best. And so there, you might say, well, okay, that technically got the best fitness, but implementation wise, I actually like this other one that's in here a little bit better. There's like kind of a hidden second objective that wasn't met that you can kind of then filter through those. And then also, maybe you look at that other population and it gives you some idea of, does this look like things have converged? Does it look like I should have ran my GA for longer, and so on and so forth? So it can be a nice diagnostic utility. But then if it hasn't terminated, then you go back to the selection step. And then there is a kind of an advanced section that if we have elitism, which I'll talk about here in a second, then this is where you would also in between before the selection is you would update elites. And so this is optional. So you find that some evolutionary algorithms, genetic algorithms have elitism, which we're going to talk about. Some don't. So that's why I'm just putting that kind of in red with the dashed line. So this is where that would happen. But for now, this is the basic flow. So population, pick the best parents by fitness, choose which parents go on to reproduction, reproduce from those parents to fill out the rest of the population, and iterate. So what does that population look like then? So if basically we start with, so we've got this population, we've got M individuals, and it's always, in this simple GA, it's always M individuals. And so of those M individuals, and this is in our old population, then what does our new population look like? Well, it's going to have our parents and M minus R offspring. And then if we have elitism, so maybe I'll move this over just a little bit, or maybe I'll do this, this will be easier. So this is our new population. And if we have elitism, then there's going to be E elites. And this is, if elitism is used. And so we'll get over, we'll talk about exactly what that means, but just putting that up there so that we know that it's available. And so when we talk about reproduction, then these parents, these are the so-called breeding population. And they're the ones that we will choose a subset of them for crossover and mutation. And I'm going to, again, go into more detail here. There are different variations of the genetic algorithm. Like, for example, in MATLAB, the way they implement their GA, then our parents go through crossover, but they don't go through mutation. There's they basically have offspring due to crossover, and then they also have individuals in the population due to mutation. So they've decided to separate those out. And there are probably small effect sizes of these choices of whether you mutate the offspring or you mutate from parents. They all that's probably so small that it kind of comes out in the wash because it's basically the same structure, but you can definitely make different choices about how you do some of these orderings. But I'm going to just kind of go with the ordering that you read about in the text for simplicity here. So in this reproduction step, then the idea there was that we you choose our parents, and then from the our parents you choose a subset, say based on probability, PC, for breeding, and then you choose pairs from the breeders and crossover, which we'll talk about in detail here in a second. And then you mutate the resulting children or offspring, and that's how you fill out these M minus R offspring. So that's the high level overview before we go into the details of uh, crossover and selection. Yeah. Hmm. You just fill them out. So you say that um, you this is a hyperparameter R. M is a hyperparameter. So you're saying some fraction are always the parents, and then the rest you do this process until they're filled. So this here is repeat until generating M minus R offspring. Mm-hmm. Mm-hmm. Yeah, that would be the case. Is it like so however, you might have three parents and not all of them necessarily, I mean, might be selected for breeding. So there might even be a subset there. But yeah, from those parents, you're going to then select a pair, put them together, have them reproduce. That will generate two, and then another pair, and that might be the same pair. It just randomly, and that'll generate another two. And so you always generate two offspring at a time until eventually you fill out all of them. And you might have to discard an offspring because you always generate two at a time. Well, we'll get into the crossover operator. I was going to talk about selection first, but I guess we can shift to the crossover um, first. So the crossover operator or operation, there are different forms of crossover. The basic idea is that if you've got two parents, so two candidate solutions, so two parents, candidates. And so this one is going to have x11, x12, all the way up to x1. I'll just create an intermediate here, k, all the way up to x1, however I said, n genes. And then this one similarly is x21, x22, all the way up to x2k, all the way up to x2n. And so we're going to talk, there's different forms of crossover, but if I were to do a 1 point crossover, then that would mean that there would be a gene here that would act kind of as a pivot point. And so in this 1-point crossover, then basically I might say that they keep everything, the offspring keep everything from the parent's left side of this point, but then they swap everything here so that you end up producing two offspring. So Y1 will look like it will look like X1 up to this point, and it will look like X2 to this over here, and Y2 will look like X2 to this point, and then X1 from this point on. So this is like X1 from 1 to K, X2 from 1 to K, and this is from X2 K plus 1 to N, and this is X1 from K plus 1 to N. So it's maybe easier if I color them. So if I were to color X1 all yellow and X2 this kind of pinkish color, then the offspring would end up having the variables like this. And this process just always, it takes two parents in and it generates two offspring out. And then these would then be added to those M minus R, and then the process would repeat. Mhm. Go ahead. Well, yes. I mean, yeah, it's absolutely like so. I mean, the R parents are basically copies from the original generation. If they maintain high fitness in the new generation, they'll be very likely to be put back into the parent population. So they may or may not actually be selected for reproduction, but they I say selected for reproduction. I feel like sometimes it's actually easier to think of it as clonal and sexual reproduction. So there are some offspring that are direct clones of their parents, and there are other offsprings which are sexual recombinations of different parents. And it is definitely possible for a clonal line to, if it maintains high fitness, to just keep going on. So, though, to come back to the same solution, I mean, if you had very deterministic crossover rules, for example, then you could have some weird thing where if you're always crossing over the same point, then you might swap genes, and if they didn't get modified very much by mutation, then you'd swap them back again. But as we'll see, that usually the traditional crossover rules are it's kind of a random spots where they cross over, and that helps liberate genes from always being next to the same genes because there's always a possibility that the crossover point will be next to them and they'll be able to pop off and remix. Yeah. What do you mean you can't use real values? So like right now, go ahead. Oh, mhm. Right. That's right. Especially if that's if you've got mutation in particular, you're adding a little bit of a real value on top of these other, it's got a bunch of floats and you're adding a bunch of things, and it's very unlikely, it's the second law of thermodynamics. You're not going to be able to come back. But yeah, if things are discrete, then you potentially could come back. But there's a lot of randomness, which is why there's sort of a lot of genetic drift possibility actually, in these GAs, which kind of prevents, revisiting the same solutions unless they're super fit solutions, and so natural selection keeps bringing you back to there, which might be totally fine. All right, but we'll get to, so this is just an example, um, rough example, but we're going to get to the specific crossovers here in a second. But let me deal with selection first. And I also wonder if I should mention, because about this floating point thing, is that, yeah, maybe I'll just at least mention it here since they brought up the floating point numbers, is that as an aside, genes can be place values of numerical representations. So you could have a gene like X is a float, and and its particular allele is 3.141. Or you could actually break that up into multiple genes, where you could say that X1 is 1 because it's positive, X2 is 3, X3 is 1, X4 is 4, and X5 is 1. So this here is a sign value. It's either +1 or -1. And then here's your tens. Here's the tenths. It's your hundredth value and your thousandths. So you can break things up numerically as well. And so this, if you did this, this actually allows for crossing over in the middle of your decision variables. So you could actually swap the most significant part of your decision variable with the least significant part of another decision variable. And this can be binary as well. So a lot of times you see depictions of the GA, and people will depict genes as bits, zeros and ones, and then they'll show crossover in between the bits. And that comes from, there are GAs that was once upon a time a traditional way that they were implemented, is just long bit strings of zeros and ones that were then crossed over in all these places, and then you later then reconstructed whatever numbers were being represented by those bit strings. But the actual genes behind them all were just zeros and ones. So you can break these things up as well. That is another way that you might do this, and there are advantages and disadvantages for doing it this way. It's going to be a lot simpler if you can just think of your gene as floating point here, but it doesn't seem very natural, because we know that our genes are these digital entities that take on these four, that are nucleotides, sorry, are these digital entities, and our genes you're formed from these codons, these sequences of codons, but overall everything breaks down to eventually there are these nucleotides, which are these bits. And so that is kind of inspired by here. So here, what's kind of interesting is if the mutation can, when you think about mutation here, when you mutate this value, you might add a random number to it. Here, if you mutate this value, it's a much bigger change to your decision variable than if you mutate this value. So the same mutation operator that's just adding, 0.01, plus, it's, plus or minus uniform random noise with a width of 0.01 or something like that. If you add it here, it does very little to your decision variable, but if you add it here, it's much bigger. So there's weird the way that you represent your genotype can completely change the search dynamics of the GA. Okay, so questions about that all sorts of ways you can represent genotypes. Okay. All right, so let's move on into how to choose our R breeders. Which is our selection operator. So there's three common options. And that's going to be our fitness proportionate selection, ranking selection, and tournament selection. And we're going to see the reason they differ in their sort of intrinsic selective pressure, but all are tunable. So as I hinted at in previous times, there's this balance between selective pressure and drift and mutation and getting all that stuff right. So when you choose your hyperparameters or you choose your selection operators, what you're really doing is you're choosing the selective pressure, how sensitive you are to small changes or large changes in the objectives. And so these are different ways to do these provide different sensitivity to changes in your optimization objective, but they're all tunable in the way in which how they sense those changes. So we're going to start the simplest one, or I don't know what to say simplest, but the one that people implement the most. I think it's the one that pops into the mind most quickly is fitness proportionate selection. Proportionate selection, sometimes called roulette wheel selection. And so the idea here is that, and by the way, remember, fitness F is a non-negative. And in fact, it arbitrarily, we could say, or strictly positive. So in your mapping from little f1 to big F, it's assumed that you know enough about little f to add something to it or to manage to stretch it out, squeeze it, somehow you get from little f to big F such that for all genotypes you could possibly have the GA walkover, big F will be, and let's just for simplicity say strictly positive. So that might not always be easy to do. So you might have to do some nonlinear scaling. You might need to run things through some sort of special function. But for most fitness objectives, you might know that the most extreme fitness is going to be negative, 5,000. And so I'm just going to add 6,000 to all of the extreme of optimization objective. So I'm just going to add 6,000 to it, and then that becomes my fitness function. So you have transformed, so I'm just saying you've transformed your fitness or your optimization objective to be strictly positive. All right, does that make sense what I'm saying here? Just, okay. And so once you do that, then we can define a probability PK um, of the fitness value for genotype K, for individual K, that is just well, it's proportionate to its fitness relative to the sum of all of the other fitnesses. So we're saying individual K's fitness is here, the sum of all the fitnesses is here. So we're forming the probability that you get into the parents is just how do you compare to the total fitness? So this is the probability of individual K selection or selected for our parents. And so the idea here is that you can generate these these M probabilities, and you can put them on a line for, or however you'd like to do this, but so like the simplest way to do this was to just create a line here where you've got, P1, P2, P3, all the way up through PM. And then these will all sum to 1. So then if you draw a random number, R, which is from a uniform distribution between 0 and 1, then it's going to fall somewhere in this, it's going to fall somewhere between 0 and 1. And if it falls between 0 and P1, then you select individual 1 for the breeding population. If it falls between P1 and P2, you select individual 2. If it falls between P2 and P3, you select individual 3, and so on. So that's what we mean by a roulette wheel selection, is that I've basically taken a roulette wheel, a pie, and I've put it into a number line. So I've just taken the pie and unrolled it so that it's a number line now. And now, instead of dropping a ball in the roulette wheel and seeing which pie slice it drops on, I've now thrown kind of a dart at this number line, and I see where the dart falls in. So, I mean, maybe I should have drawn these out as areas down here. So I could have said, like, well, I've got a number line here that goes from 0 to 1, and the width here is P1, the width here is P2, and so on, all the way up to the width here is PM. And so, and this again goes just to 1. So if I draw a random number uniformly distributed between 0 and 1, it's going to land in one of these regions. And if it lands in the region, then I end up choosing that parent to go into the breeding population. So I do that R times. So just repeat R times. To get our parents. Does that make sense? So that is sort of a conventional way to do roulette wheel selection. The downside of this is that if, I guess I'll mention it on this page here, but if f of xk is very large relative to other fitnesses, then our parents get flooded with genotype K. So this is what we mean by it has high selective pressure. which means that if you have a difference in fitness, then you are going to dominate the next population. So very rapidly, you purge alternative solutions from the population because one solution happens to be so much better than others. So if you're confident that there's only one good solution in your decision space and you just don't know where it is, but once you find it, it's got to be it, then this is a great way to find it fast. But if there's a bunch of local minima or local maxima, how whatever, which whatever you're doing, if there's a bunch of local optima out there, then if you happen to put a bunch of individuals out and one of them gets close to one of those local optima and the rest are less than it, then they'll be quickly flushed from the population. All the parents will look just like the one that's close to that one local optima, and then they'll start fine tuning and you'll just find the local optima. So that's the downside of this high selective pressure, is that it can lead to premature convergence. And so one solution is to implement fitness scaling. So basically, you've in your mapping, when you form your F, F of your genotype is going to be equal to some scaled function around your fitness objective. So here, this is a scaling function, which squishes or reduces large fitness different or objective differences. Sorry for the scribble here. And so that means that if you know that your fitness objective might lead to this, well, one thing that you can basically do is squish it all down so that the possible difference in the fitness realized by the algorithm will never be that great. And so then there's always some possibility for solutions that are not quite as good to make it into the breeders. And that's one way to reduce the selective pressure. It's not an ideal way to do that because there's a bunch of different ways to choose this function. So how do you do that? So, it's like, but how to pick scaling function? That's not trivial. So that's why we have the other ones, is that they provide a much more natural way to do effectively fitness scaling that achieve the same sort of thing, but they don't require coming up with yet another crazy hyperparameter that you have to introduce. All right, and so I'll just hint at one of those now, and then we'll finish this up next time. So, alternative ranking selection. And this basically means that you're going to rank things by their optimization objective scores, and then their rankings effectively become their fitness. So then it actually doesn't matter how much better one is over the other, the order is all that matters. So basically you're replacing objective values, objective scores with order in a ranking and using that for fitness. So rather than going down through, so for example, what I'll do is I'll like rank in individuals to reproduce each with copies proportional to rank, and then 3, draw uniformly from pool to produce our parents. And so I'm just leaving that up there very quickly, and then we can conclude here. But the idea here is if you're top ranking, then you have to come up with, how many copies are you going to give to each rank? But you basically say the top ranking one, I'm going to give 50 copies. The next ranking one, I'll give 49 copies. The next ranking one, I'll give 48 copies, and so on. At that point, it doesn't matter exactly how much better the top one is over the other one. It's just because it won the top rank, then it gets everybody who's in the top rank, regardless of their fitness value, gets the same number of copies. And then those go into this pool, and then you just draw randomly from that pool. So genetic drift can apply to here. And then that's how you get your R parents. And that greatly reduces fitness, selective pressure. All right, we'll pick up there next time. And yeah, so that's, I guess, have a good weekend. Mhm.